main point is we're starting, and I have the privilege of interviewing Turing Award winner Alan Kay, the father of personal computing and all around a great guy. So this is the audio setup here is extremely fragile, so I'm going to yell and hope that you can hear me, because if I put a microphone on, all hell breaks loose. So we're just going to start. And I have a whole bunch of questions for Alan, and then people can put their questions into the Discord and or ask in the audience. We'll kind of intermingle these as we go along, but I'm going to kick this off. Alan is famous for these, I'd call them aphorisms, and one of them that especially I'm especially fond of, and I think would be useful, especially to younger people who are not familiar as they should be with Alan's work, is this idea that point of view is worth 80 IQ points. And I think, Alan, if you could explain what that means briefly, and also asking for a friend, how do you acquire these points of view?
Well, of course, I didn't specify the sign bit.
Yeah.
So that's the first thing to... The basic idea of an aphorism is it's a kind of lie that if it's done correctly, it points one's view in a positive direction. But if you try to take an aphorism apart, it quickly becomes ridiculous. So, but the basic idea, actually the basic idea behind aphorisms, because I don't think in terms of them, came about at Xerox PARC when we first had to learn how to communicate with Xerox executives. And at some point we realized they were not paragraph based. And I would call a lot of the people at Xerox PARC kind of paragraph. We liked whole paragraphs, not even sentences. And so the question is, what can you get across? And the answer is, well, proverbs. Proverbs are the shortest and earliest form of stories, and they have the ring of truth to them. So I started making up proverbs, and point of view is worth 80 IQ points is one of those, trying to draw attention to the idea that every culture on the planet has accumulated lots of knowledge. One of my father was Australian. I grew up my first few years in Australia. My father was a great admirer of the indigenous Aborigine people in Australia. And he pointed out to me when I was a kid just how much they knew. And their point of view was different, but they could survive in the outback and we couldn't. And that made a big impression on me. And of course, I think anybody who's looked at the history of science, and particularly the transition from science as gathering knowledge to science as a collection of methods that in part try to get around the noisiness of our bad brains, realizes that these things called paradigm shifts could also be thought of as difference of points of view or differences in context or perspective. And boy, looking at something that's right in front of you with a different perspective can actually reveal things that are literally invisible to you, because our brains cannot see until we've learned how to see something. So this has been shown. So we have this improper notion that we actually see things out there, where in fact we learn things and seeing is done inside, and it's often done in a faulty fashion. Yeah, so one of the problems with that aphorism is you have to relax and not do short-term thinking in order to use it, because the relaxation gets you out of your initial reactions to things. So this is what basically what current day AIs, so-called AIs, do wrong, is they react quickly and usually wrongly. So the real thing is to try and find ways of not reacting quick. I write things down in a notebook and then never look at them again. That way I feel like I've served my fast ideas in some way. I have many of these notebooks. I have no idea what's in them. But basically, after a while, you start having ideas from a different viewpoint. And sometimes those viewpoints can be really powerful. Often the viewpoints come from looking at, like a big one for me was going from looking at simula, the first simula, as a better old thing to almost a new thing. So if you look at simula as a better old thing, you wind up eventually with something like C++, which is in fact the way C++ happened. Specifically, that's what Bjorn said in his first C++ paper. He was trying to do to C what the simula people did to algol. And you wind up with something like abstract data types. But if you take the other point of view, is what if this is almost a new thing? So what it is transitional. What does that mean? And that will get you to a completely different set of thoughts.
So, Alan, one of the things you mentioned brings up another one of the questions I had, which I was going to save for later, but it's a good segue. You talked about LLMs. So a commentary on the new wonder of the world and the AI situation. Yeah, maybe you can speak to that.
Well, I'll give you a parable. So in the 20s, actually in the early part of the 20th century, rays were a big deal, X-rays. So scientists looked for rays, and a scientist in France found the N-ray. And over a period of 15 years or so, more than 1,000 scientific papers. You can look this up in Wikipedia, by the way. More than 1,000 scientific papers were written about the N-ray. And then finally, several scientists proved that there was no N-ray. So this is used actually by both sides. So people who don't like science say, look, science is just another belief system. Look at the N-ray. It has its fads and all this. And people who are for science, like I am, say, yes, but this fad only lasted for 15 years or so, and then the methods of science got rid of it. Try and do that to any religion that's around today. So you can look at these things in both ways, but basically human beings like to be right. We rationalize rather than think rationally. We have confirmation bias. We've got a billion ways of dealing with the bullshit that goes on in our heads. So the real question on any of these things, and I mean, another aphorism is the softer the science, the tougher you have to be. So if you're in a soft area, like if you're doing social science or you're doing something like so-called AI, you have to be really tough about it because it allows our tendency towards theatrical thinking to intrude and impose our own beliefs and hopes on it. Right. So I think it's really tough being a good scientist in the social sciences. And I think this is the case for the current setup. That being said, if you look at Daniel Kahneman's book, Thinking Fast and Slow, you'll see in the beginning, he says, I have to tell you that I'm going to make use of two expository fictions. I love this phrase, expository. Expository fiction is a lie that helps you tell the truth. So it's like Picasso's definition of art. And Kahneman says, look, even if you take the billions of neurons in our brain and the trillions of connections and simplify them down to hundreds of modules. It's still too complicated to write a book about. So what I'm going to do is I'm going to call everything that results in a fast reaction, no matter where it is or where it came from. I'm going to call that system one. And he says it's not even a system. And I'm going to call everything that goes much more slowly, wherever it came from and wherever it is, I'm going to call it system two. And I'm going to see how much ground we can make with these two fictions at puzzling out some of the things that might be going on in our brain-mind conglomerate. And one way of looking at what happened is in the early days, the people who were interested in what we now call, artificial real AI or whatever, general AI. But in the early days, they looked more or less directly at the whole thing. And then there was the AI funding winter. And the thing that got popular was the lesser part of the problem, which is doing perceptron-like things with a few more layers. And the fact that Kohonen had showed that a form of matrix algebra was isomorphic to what perceptrons were made the papers look a lot more scientific than they actually were. And all of a sudden, you've got what academics really crave and academic funders like NSF really crave, which is the trappings of respectability. And I think, and it's not that, look, I have a stage 4 cancer. And the so-called AI, the stuff that isn't really AI, is actually helping me because it helps radiologists look at my PET scans every 3 months and try and figure out what new interesting source of sugar metabolism is going on besides all the stuff we can see from the brain and the bladder and so forth. So I'm happy for what the stuff can do. But I think everybody in computing should be unhappy for what is claimed. And if there's anything in the word science, if computer science is not a complete oxymoron, then scientific minds should be delineating what it can do and what it can't do. And smart people like Doug Lenat, who unfortunately left us last year, realized, well, what you want to do is, Kahneman's model is actually fairly good because we need correlators, whereas Judea Pearl calls them massive curve fitters. We need those because coincidence detection is the start of trying to find out whether the coincidences actually have any meaning. And so that's a good thing. But if you don't have the system two, to be careful about it, you're going to get what humans have had for a couple of 100,000 years, which is superstition and making up stories and all of these things. And so one way to think about it is just demand that the funders fund something more like a system that not only can propose things, but can also vet them. And I think given that any 12-year-old can set horrible things loose on the internet these days via free software, I think having some form of vetting system for almost anything that goes on the internet is actually a good idea. But I think that's out of the scope of this discussion.
Okay, awesome. So now I'm going to ask a question that I have to ask even if some people are less interested, but it's the perennial small talker question, right? Which is basically, why has Smalltalk not been as successful as small talkers think it should be? And do you think that's even a worthwhile question? No, I suspected that.
No, but of course that won't keep me from giving you an answer.
Well, you could also. So my backup was, well, why isn't it a meaningful question? So you can you answer whatever you want to answer to that.
Well, So actually, I missed my chance to say at the beginning of this that I should be interviewing you, and I know Dan Ingalls is here. So me interviewing you two guys would be interesting also. Um, and the complexities of which languages get chosen or not are sometimes even accidental. So I've never really actually tried to figure it out. But I think that part of the problem had to do that Smalltalk was successful, highly successful in the 70s. There was nothing like it in the 70s, but it was highly successful because Xerox PARC did what I think is the correct thing, which is it built hardware and software that work together. So we thought of whole system, the whole Xerox PARC, the ARPA community thought in terms of whole systems. And so it was not unusual to think of processes that would be really helpful and interesting and to think of them in terms of some hardware-software combination. And PARC built all of its own hardware precisely because it did not want to try to do all the workarounds and even dead ends that were present in commercial software. And we were arrogant or confident enough, depending on how you look at it, to think that we could actually do hardware and not just do it, but to do it in a timely enough fashion to allow the main enterprise at PARC to still be software. And that happened because of people like Chuck Thacker and Butler Lampson, and a lot of stuff happened. But basically, we wound up being able to make the equivalent of a supercomputer for each person at PARC, including all the secretaries and so forth. And because of the way the microcode engine on this machine was designed, and purposely, because we knew we were going to be doing virtual machines of various kinds on it, we could actually make the equivalent of custom hardware before the fact. And, there's a lot of history that goes behind this desire. Part of it, as you know, as well as I do, goes back all the way back to the Burroughs B5000. And it's the fact that it was a byte encoded virtual machine in hardware. And it was a more general machine than either Algol 58 or Algol 60. It was more like a Simula machine before Simula happened. So it was a genius level thing. And the one lesson to be learned from it, besides the fact that this is a good way to do things, is that microcode really would have helped the B5000. And of course, Bob Barton, who was the designer of it, the next thing he did after the B5500 actually was microcode. I think that was called the Burroughs 1700 or something like that, because basically in order to deal with learning curves, you need to have some wiggle room in the lowest level of the machine. And the Burroughs B5000 was wonderful for what it was designed for, but didn't have enough wiggle room. So with these microcode engines, which were a great idea for their time, like today you would use something like field programmable gate arrays that would plug into blade servers or something like that to allow you to make a synthesis, and you would have languages that would allow you to program all the way down to the actual gate level if you needed to, because why not?
Okay, now I have, at some point we'll bring in the audience, but I have one question that I don't want to miss, which is sort of a larger question, and that is, looking back, what would you have done different than, in terms of your career, and you've had a huge impact and so forth, what are the things that you might have approached differently or done differently?
Well, I like John Lennon had a great comment, which is life is what happens while you're making plans. So if I will never write a memoir, but if I were to, it would be called something like An Accidental Life. I never wound up making a plan. It was like a leaf on a stream going down, turning around, and occasionally bumping up against shore, and there were interesting things, and then back on the leaf again. Uh, so I wouldn't change my plans since I didn't have any, but I did learn a few things. Um, a couple of them I should have known. So, but I think one thing that's hard for any kind of funder today to actually appreciate is what the word research actually means. And in an aphorism, research means you can change your mind. So whatever goal there is to turn up something new and interesting. Bell Labs had signs. This is back before the divestiture, but you sign on a stairwell or a sign on the wall that said, either do something really beautiful or really useful. That was what the sign said. And the people who funded Bell Labs did not care which. They wanted something extreme, and it could be in one direction or the other. They didn't care. So a lot of good things came out of people following their nose. And some people had the nose for practicality, and some people had the nose for beauty, and some people had both. So I think that, but the one thing I came to appreciate about Park, and particularly our group at Park, is the thing is, if you're going to have a group, you might as well have the best people. So you basically want to have people that are better than you are. Because if you can be friends, drink enough beer together, basically, you might be able to synergize these different talents. And that fact, if you get synergy, is going to give you something. It may not be what you originally thought you were out after, but it can give you something that is really, really interesting. So you mentioned Smalltalk. So it is certainly one of the most interesting computer artifacts done in the 20th century. It stands out even today in many different ways. And so I think one way to think about these interesting artifacts are similar to the way I think about the first Simula, which was, it wasn't that it was perfect and the first Simula didn't really succeed either. We could ask, why didn't Simula make it, especially Simula 67? It was pretty darn good. And it was really, on the other hand, it was really early. It had all of these different barriers that we're used to coming up against. But I think that if you're doing your job right and you're actually doing research, you're creating things that have enough integrity and interest to still be mentioned, as we are doing right now, more than 50 years after the fact. Right? I'm being asked the question about Smalltalk, and the guy who made it really possible is sitting in this room. So we should follow up by asking him. But the realization I had some years later as a research leader is, if your strength is starting things and you're partially looking for completers to get the thing done, let them complete. Right? If you have more ideas, go and start another group. Don't try and dissuade because completers have their own dynamics, their own sense of aesthetics, and I didn't realize that at an early enough point. And it turned out that it was good that they completed, because the actual insights needed to have the first success, stuff that I considered successful with children, didn't happen until about 25 years later. It wasn't until Disney in the late 90s that, and this is your point of view is worth 80 IQ points idea, I realized I had actually gotten sucked sucked into my own Kool-Aid, because mathematical background, it's nice. Math is really nice to build entire universes from tiny little universal principles and stuff. And Smalltalk is certainly an interesting example of that. The thing that worked with the kids was actually the opposite idea. Is not the way mathematicians think of it, but more the way scientists think of something like Maxwell's equations, where you basically, you have, you can put it on a t-shirt, but it is a pretty complex combination of powers. But the power of it is, once you have the t-shirt, pretty much everything else in the electromagnetic realm is just parametric. And so the thing that worked for a children's language was to give them, instead of a minimal object that you build everything out of, which was not in the children's space, was instead to give them one universal object in which everything interesting was parametric. And there are a few other ideas in there, but I was struck by how opposite the two ideas actually were. And of course, thanks to Dan and Smalltalk and Squeak, we had Smalltalk and Squeak to do this different set of ideas on, and so it rode on top of Squeak Smalltalk. So the whole story had a happy ending from my point of view.
Happy endings are good. Maybe people
It helps if you're happy.
That's true. That's a point of view again. But do we have audience questions? Because people might be tired of me asking questions. Otherwise, I can go on forever, but yeah. Okay, so the logistics here are very tricky. You need the microphone so it goes to the stream and the recording, but then I need to repeat the question for Alan because the microphone doesn't go to his audio, and so we just have to get this right. So, oh, you've got it in writing. Okay, where is it? It is this one? Okay. We are still talking about Smalltalk and Simula today. Does this indicate that these ideas and artifacts have integrity, or they are just very compelling superstitions? Oh, I like that. How can we tell the difference?
Yeah. Well, look, on questions like this, it's sometimes good to go to neutral ground. Like, what kind of scaling has happened over the last 50 years? What programming language has survived the scalings of Moore's law? And if you look at the scalings of Moore's law in hardware, it's happened mostly by not inventing new good hardware architectures, but by recapitulating old architectures, basically doing away with a couple of levels of design that really are needed in order to just get the design rules a few nanometers smaller. So, but if you apply the scaling that's happened to programming languages, the shocking thing is that any programming language, Smalltalk or not, done back in the late 70s or early 80s, is still being programmed in today. And in fact, it's shocking to me that hardly, at least from the outside, I don't consider myself an insider anymore, but from the outside, the progress in programming language design looks to be close to nil. And that is completely different from the 60s and 70s, where paradigmatic shifts in the ways of thinking about programming were happening every 5 or 10 years or so. And what's happened since then has been way too much optimization, to me, of the wrong kind. So I would expect, for example, not to ever see the news that we got from CrowdStrike, What a terrible name for a company. Worthy of George Orwell. But how could that happen? Or Facebook taking itself off the internet, including its own computers, for more than a day because its 9,000 unit tests did not include one that said, hey, our main large goal is to be on the internet and serving people. Or an ominous one like the Boeing 737 MAX autopilot that crashed two planes full of living people into the ground because of some bad decisions of management and engineers going along with it. So, I mean, I would expect to see software that is actually primarily set up. Yeah, let's take another analogy to the Hippocratic Oath. In the middle of that is the phrase, above all, do no harm. So that's the main admonition for doctors. And of course, they've done a lot of harm over the years, but they're, in theory, trying not to. But for engineers, the equivalent of that is the bridge must not fall, the building must not cave in, the airplane must not crash. And we don't have one for software, which should say something like the system should be safe, the system should not hurt people. And I don't know of much, if any, software that is wrapped with the checks and balances before actual actions in the outside world can be done. And I would expect this, and one of the many things I learned from Butler Lamson years ago is that if you're interested in security and safety, don't try and bolt it onto your system afterwards. And this is like the same principle for user interface. If this thing is eventually going to be used by a human, start off with a user interface, because it is really hard to put a good user interface on sheer functionality after the fact. This accounts for most of the bad user interfaces in the world today. So, just as an outsider now, things look completely ass backwards to me, and they don't take into account either the scale or the reach in both time and space. For instance, should the stock market be allowed to do lightning trades at the rate it is allowed to do? As a systems guy, I would say absolutely not. Part of the stability of the stock market and the way it actually worked depended on this thing called the float, which had to do with the time for messages to get through the system. If you change the message rate in a system, you're going to change how the system responds to various kinds of stresses. So, yeah. So the reason I didn't have a direct answer for Smalltalk is, I love what we did back then, but a lot of the things we did back then were, in anticipation of some of the scalings that would come ahead. But if, as you know, as somebody who's used Smalltalk, we could have made the interior of an object much more like a real world. And we didn't because we didn't have enough space. We resolved to be careful about how we did various kinds of things. And we got around things and still came up with some elegant looking and working software. But as you expand outwards, you start getting into problems like, for instance, putting labels on things gets less and less useful as you expand out onto the internet. You want to find things by descriptions and by matching descriptions and matching behaviors rather than trying to match up names. So the whole idea of interfaces actually has to be different. You need something perhaps more like what Gilad was trying to do with Linda, right? And what you would do there was to try and understand exactly how you're going to deal with semantics that you can recognize but don't have a name for. And like another thing you could do, just as an example, is you could say, here's an object that is going to be very helpful, but it makes use of global resources. So the worst thing you could possibly do is have a variable to stand for those global resources, right? Because what you really want is to stick an object in each one of those variables whose job it is to first imitate the global resource so you can debug your main object. But it can also, when you ship the object off, it can also adjudicate with what the global resource is trying to link you up to. So these are just elementary system ideas that arise when you think about what are the actual problems of scaling. And I would love somebody to show me a system that does even these simple things rather than showing me millions of lines of very, very rickety code.
So
I'd like to see, yes.
I wanted to latch into one of the things you said when you talked about safety, and there are a lot of people here who are concerned with safety and verification, and I cannot resist the temptation to ask you to comment on functional programming, because
Yeah, well,
that is a lot of what that community is
but
about.
remember, do you remember what Gandhi said when they asked him what he thought about Western civilization? He said he thought it would be a good idea.
Yes, it was worth asking you that.
Yeah. So, I've answered this question a few times in Quora, but to me, the real idea about thinking in terms of functional relationships. So let's not use the FP term, but in thinking about terms of functional relationships, it means that you can reason from what John McCarthy called a situation back in the late 50s, from one set of states to the next set of states. That was what he wanted when he was trying to do this software interface called the advice taker. And it was the desire to make this advice taker that caused him to invent Lisp as a programming language to program the advice taker in. And in both cases, McCarthy realized that you had to deal, in his terms, because he was a mathematician and a logician, he would have to use something like a modal logic in order to reason about things happening in the real world, namely that, like on Monday, the robot is in Philadelphia, and on Tuesday, it's in Boston. And he realized that unless you included a timestamp for any fact, and that gives you a modal logic, gives you a temporal logic, you can't actually reason about most interesting things in a computing system, because the whole idea is to get state to change and evolve over time. So McCarthy called what today we would call a world, he called it a situation, and he called these pseudo timestamps fluents. So this is back before the tyranny of semaphores and monitors, and this is a really great set of ideas, because basically what McCarthy was saying, look, what we were doing on the computer is simulating models. And the thing we're basically doing wrong is we're letting the CPU tell us what time it is. And what we want to do is we should simulate time also. We'll use pseudo time. And by the way, the first Simula did this. The way Simula scheduled its processes was what it called a scheduling set. And the scheduling set each process in this set of things to be scheduled was marked with a pseudo time when it was supposed to happen. And the way Simula worked was when it would get done with the actions for a particular time, the next thing in the scheduling set was the next actual time. So it just immediately go to that time. And so it computed in between time changes. So this is a great idea. And Simula 1 actually had a predicate that would tell you if somebody else was scheduled for the same pseudo time you were in.
Yeah,
because that would allow,
yeah, go ahead.
right?
Go.
So, yeah, so this, what McCarthy was able to achieve here was a way to think about functional programming in a much stronger way than most of the thoughts since then, which are way too much like regular mathematics. So McCarthy's idea was you have a situation, which is a set of stable stuff, and you can reason about it. And by the way, you can use it to make your next stable situation. And if the mapping between situation 1 and situation 2 can actually be functional, because you can have, with pseudotime, you don't have any race conditions unless you permit them. And so McCarthy was thinking about, and when you throw objects in, you basically think of a sea of objects that, if they can really send messages to each other, they are actually compatible. And in an ideal system, you would actually be moving the sea of objects from one stable situation to the next stable situation. So this is in keeping with some of the ideas that were done with databases and transactions, but it's applying it to whole systems. That if you can think of terms of, then you actually wind up with something where you're making a model. You don't have to use distortions of an idea like monads in order to do. You have state changing, but the state is changing the way it does, say, in a bank account. No race conditions are allowed on a bank account, and things are set up so that at any given time, you can do accounting on your file structure across all the files, and just exactly what it is. And the thing that's the problem in programming language is that I think people don't really understand objects very well, because they're still thinking of them as being data on the one hand and process on the other. And you really have to link them together in a stronger way. And then you get a functional programming that is absolutely functional, absolutely can be reasoned about, and would be a lot of work. But for instance, Alex Worth, who I think gave a talk on Monday, and Yoshiki did a system called Worlds. Yoshiki Oshima did a system called Worlds, which tries to show how you can deal with various forms of undo at different timescales. So if you think of this idea of going back down through the world lines, how much of the past should you retain? What does it mean to go back? And so forth. And the grain size of things, it means it's going to be like sorting, where you have different methods for sorting a few things and different methods for sorting large things. The predicate for sorting is the same. And the same idea for functional programming. You have basically a predicate for what it actually means to move from one state to another in a graceful way.
Cool. I was looking for a definition for monad for years. Thank you for that. I think we should, we probably have other audience stuff, right?
We should probably do it.
Oh, from the audience? Yeah, however we want to do it. So a reminder again, microphone, and then I have to repeat the question. So questions from the audience. I don't think it's doing much.
Can you?
It's not doing much.
Can you press it once Hi, Alan.
Can you hear any of that? I'll repeat it anyway.
Okay. How much of this lack of progress that you lament has to do with learning difficult to learn things? As you said, the future of reading depends on the future of learning difficult to learn things. So how do we learn difficult to learn things in order to make progress?
Okay, I'll try and repeat that.
Oh, I got
you got it?
that.
Okay, excellent.
Got it. Yeah. So that was a paper I wrote for a book, chapter in a book years ago about the future of reading. And the title was "The Future of Reading is the Future of Learning to Learn Difficult to Learn Things." So, meaning what reading and writing is about, in being serious about it, is having something interesting to write about that's then interesting to read about. And one of the ideas from back in the 60s was that the computers were going to give us an additional way to represent complex things like dynamic systems, processes, representing communication systems, and so forth. And that the media for writing about this had to include, like right now, when I write something on Quora, I can write in words, or Wikipedia, I write in words, I can stick in a picture, maybe stick in a movie, but I can't stick in a computer example, even though people are reading Quora on a computer. So if you want a definition of nuts, this is even better than Einstein's idea of crazy is doing the same thing over and over again and expecting something different. I mean, it is literally crazy to be confined to old media when you're on something new that has new ideas that need to be experienced in order to be understood. So it's very, very difficult to actually write about computing in computer terms, right? So that's a simple idea from it, and that's one of my biggest complaints. So to try and answer the question, I'm afraid I think and this is an old fogey reaction, but I think one of the problems that seemed to be pretty apparent when I was doing some teaching at UCLA to both undergraduates and graduates was, wow, what a terrible waste of these kids' lives to have an undergraduate degree in computing. Because think about what they could actually be learning if they weren't taking up all this time learning almost nothing interesting. And that learning they would do would actually make them much more sensitive to the new things they could be learning about. And of course, that's not the whole story, because let's face it, things are very different than they were in the 60s and 70s, especially with regard to life-affecting things like, for instance, real estate prices, which are not counted in inflation, and in California have been more than a factor of 10 over regular inflation. And this has changed the goal structure of lots of kids going to college. And they're not getting much in high school. So college is doing a lot of the work that high school used to do. And because of this vocationalism, it is not doing what college used to do, which is to be the keepers of the flame of ideas, of what it means to be involved in ideas and making ideas and thinking about ideas, and above all, criticizing ideas. So one of the things I used to do in my classes, and if I were here present, I would try to get people in the crowd to really criticize the web and the web browser. It is really hard for undergraduates. They're trying to learn it. I'm not trying to criticize. It's crap. It's one of the worst set of things ever done. It set us back 20 years. Yeah, in fact, 20 years ago, I used to complain about not being able to do WYSIWYG editing. And people would say, well, it's, we're working on it. We're working on it. And we still don't have it. Like, for goodness sakes, come on. It only took a few years to invent it in the first place. Why is it so hard to do? So this is a little bit like the difficulty the US is having getting back out into space. A lot happened in a few years, and some combination of the will and the zeitgeist and funding and everything else has made it extremely difficult to get to the next stages. Yeah, so I think that question that was asked, I think it's the best question I've been asked in a long time, because I think in order to move forward, we somehow have to be able to criticize, even as we love. Like, I love Lisp. I had nothing to do with it, but the hours that I spent one afternoon actually going through the eval and understanding it were transformative, because it basically took a lot of ideas and made them down into this little eyeful and a brainful. And all of a sudden, it was easier to think about many different things. Now, I've had that happen a number of times, but I would never program in Lisp today, because even as I love it, it is a wonderful thing from the past. Same thing with Smalltalk. So one of the things that the universities, I think, are missing in their prime job, which used to be not only learning about what has been done in the past, but learning how to critique the past. And I don't see that spirit, certainly in the engineering schools. I think that is a disaster. And I personally don't think universities should be trade schools. Or if they are going to be trade schools, then they should have a separate department for teaching the trade of dealing with legacy programming and business. That's a perfectly reasonable trade, but I don't think it has anything to do with making computer science move ahead.
Cool. I guess we have time for probably one more.
I see a hand down there in front.
Yeah. They're working on the microphone.
So far, yes.
Or just come up here. If
No?
come here
Okay.
and just say it here. That's simpler.
Hey, Alan, do you think that there's a limit to the amount of progress we could make? Certainly, a lot of things that were common 50 years ago, or the things that were pushing the boundaries 50 years ago are becoming common: memory management, databases, everything. But has it taken this long to really absorb as a society, or do you think we could make that explosive progress that we saw early on?
Well, I think what's in between our ears is definitely finite. And I think our powers of abstraction are almost certainly finite. But it's like asking, is science the final answer? And my answer to that question is, well, it doesn't matter, because the answers we're getting from science are very, very helpful and illuminating. So let's keep on with it. I think I don't want to point. I hate to criticize without really backing it up, but certainly I think the easy commercialization that happened in personal computing in the 80s, which is a particularly tough time for languages like Lisp and Smalltalk. Because you're all of a sudden you're going to something that like a processor that's going to like something like C much more than something like Lisp or Smalltalk. And you're also in a position where something like Unix was starting to be used in universities. So right away you have, the reason we used emitter couple logic at Park was the micro engines had to be fast in order to predict into the compute into the future like we did. And this intermediate period where we had 8-bit micros and then slow 16-bit micros that could be put into machines like the Apple II and then the Macintosh, but without the amount of bang for the buck that the higher level software needed. I think if you were to go back and look at this, it actually created a desperate problem for people who are interested in higher level languages. Now, to some extent, people like Peter Deutsch and you mitigated that by finding various ways like just-in-time compilation to deal and there's tracing optimization and so forth. There's ways of dealing with a bad processor and a very high level language if you have enough memory for caching. But I think there was a huge mismatch there that effectively, you had to, for doing Lisp, there was a board that you could, on a cable, you could plug into an IBM PC that would do what Lisp did slowly but well. And so I think what happened is normal got redefined in the 80s. And from most people's standpoint, it got redefined upwards because all of a sudden there were personal computers. I think from the standpoint of the people who were working on a very large vision that like the one that Park had, normal got redefined downwards. It was like going back in time 100 years to come out of Park and into the general world there. And I don't think and you could sell them. So all of a sudden marketing people got involved, and marketing people hate learning curves. So the tendency was, what can we sell that doesn't have a learning curve, that is worth something to somebody who has some extra bucks out there? Well, why not sell conveniences? And we can sell video games. Those are two things that are really built in conveniences. People are already reading and writing. Let's sell word processors. And so you basically have this marketing level that didn't look ahead towards any new media. We're using a medium today in Zoom that does less functionally than what Engelbart's mother of all demos did in 1968. Because we cannot share the way Engelbart had sharing by multiple people of multiple things built into the operating system. I don't know of any of the regular operating systems today that has that even today. So I feel that what happened was things moved into a comfortable area of consumer electronics and toys. And that the education system, as usual, lagged way behind. And because it lagged way behind, what it decided to do is to teach the bad designs that were being sold to consumers, because that's what were out there. And so you got this perpetual motion fur farm, which, if you know what that is.
So that is the perfect note to end this session. Thank you so much, Alan. This was terrific. I could go on for a long time, but
Let us all give Dan Ingalls a cheer.
absolutely.
Because he was one of these people who absolutely went after what was just barely possible, and you were also, Gilad, going after the what's just barely possible that qualitatively changes things is how we get ahead. That's what we need to teach kids in school.
Thank you. Again, awesome. Thanks everyone for attending. Okay, take care.
Bye-bye.